Thank you, Paul. Thank you very much for the kind introduction. Thank you very much for inviting me to speak to you today. Am I loud enough? People at the back, can you hear me? Good. Otherwise, I would do the evangelist rock star thing with microphone and so I'm going to talk to you today about something that I think is a hot topic: machine learning, artificial intelligence, and which seems to be quite far removed from geology. So when you all know geology, and that's what it presents itself to us. But when we want to know more, we have to get data by drilling into it, analyzing, measuring things, and then put it together into the big picture. And most of you will know this map of William Smith, who was a self-taught civil engineer and who then connected the dots from his civil engineering project and his observations around England into the first geological map of England and Wales, which I think really was a breakthrough in modern geology. It's not just a map, it's a concept of how the Earth works. And the visualization certainly helped to understand this big picture. And then the next step up, of course, is, I would say, GIS in more recent decades, layering maps on top of each other and then doing some operations on that, interrogate the data in a spatial context, and get new insights from the data from that. And more recently, we had this idea coming up that there's actually a new paradigm of doing science. So for the first couple of thousand years, we did empirical science. We observed natural phenomena, described them, and noticed that there were recurring patterns. And then in the last few hundred years, we had the mathematical tools to formalize our observations into more general models that we could then formulate as in mathematical language and make predictions of how systems might behave. But some systems, especially geological systems, can be very complex. And if you think about the movement of water through sand or gas through sandstones, things like that, those are very complex phenomena that we can describe in a formula, but to actually calculate what happens is beyond what we can do with pen and paper. So with the advent of computation on machines, another branch started around simulating phenomena and observing things in silico, and from that gaining new insights. So a bit more than 10 years ago, with even more data and even more compute being around, some people said we are entering a new era, the fourth paradigm of doing science, which they called e-science, which brings together theory, experiment, and simulation. And so we work with data captured by instruments, we process it by software, and then we store this in computers and analyze databases and large amounts of data using statistical tools, etc. And as a geochemist, I thought, what's new? I learned this in undergrad. Is this really new? And only more recently, I thought, yeah, there's something to it, because there are tools around, computational tools that we now start using as tools, not just in the way that we plot graphs and draw lines through buckshot scattergrams and things like that, or squiggly lines, but we actually use new tools to extract patterns and stimulate new lines of investigation just from studying data. So I think the debate is still open whether this is a new paradigm or it's just new tools, but that's certainly a line of thinking and received a lot of hype in its time. So on the topic of hype, the hype today is machine learning. And of course, machine learning will cure cancer eventually. But the question is it the right tool for the problem? Not particularly in geology. Where are the fields of applications for machine learning? Which problems can we solve? And where are the limits? And this is a big part of my research, to find out what are these tools, how do they behave, where can we use them, and where do we reach the limits of those tools, and where do we lack understanding of interpreting the results. And certainly one of the things that we came across discussing this question is that in geology we deal with sparse data, and what we usually are after is understanding some phenomenon, but we observe some noisy data around that. This is a little clip produced by Neil deGrasse Tyson to explain the difference between climate and weather. So the red line is climate, the blue line is weather. And so usually we observe the blue line, but what we're actually after is the red line. And when we look at the situation in geology, it's often more like that. That we observe even less, and then we try and guess the red line and try to understand the underlying pattern and the driving forces or the principles behind it. So we're in a world of sparse data, and that doesn't really fit with the machine learning, big data, artificial intelligence things around. And so when you look at how much data do we actually need to teach a machine learning algorithm, it's actually pretty big numbers. So I found this in a tutorial as an introduction, and I thought it was a good summary. So you need thousands of examples, no fewer than hundreds. I'll come to that in a moment. And that's for not too complex problems. So if you want to train something that's quite complex, like distinguishing cats from dogs in pictures on the internet, which are quite big arrays of pixels with ranges of values, that's a hard problem, and you will need millions of examples. So if we think that when we look for gold and we look at the parameters that we use to find gold, that's a high-dimensional data space, many chemical elements, other things that go into it like geological structure and geophysical measurements and whatever you want to put into your model, it's certainly a high-dimensional data space. It's a complex problem. How many examples of gold mines do we have in Australia? I don't think we have tens of millions of gold mines that we can use as positives to train our model. So the question of, can we find the next gold mine by just throwing data at the problem? I'd say not with present-day tools, but maybe there are other ways that we can tackle this, and maybe there are other problems where we are in big data, machine learning territory. So because this is such a buzzword, I quickly want to give you an overview of what machine learning is, what kind of categories of machine learning are. So just the general Wikipedia excerpt talks about statistical techniques, learning, and without being explicitly programmed. I think those are pretty important keywords to understand what this field is about. So statistics play a big role in this, then improving the model as it goes, or teaching it, and then also dealing with situations where you don't explicitly program how the problem is to be solved. And then there's some keywords that are associated with the data mining: exploratory data analysis, predictive analysis, pattern anomaly detection, which again, let me ask what's the difference to what I did as a geochemist. So this is what I usually did. So what do the machines do? So last week I saw this taxonomy, this tree of different things that make up machine learning, also sometimes known as artificial intelligence. The specialists will tell you there's a difference, but in the media hype, that's almost synonymous. But the point here is that in science, we tend to think top-down. We make deductions, we make rules, and from that we then make a prediction of how we expect things to behave. So when you go back to the slide I showed about the research paradigms, this is certainly the second paradigm of the analytical solution. I understand how it works, I make rules to explain how I think the system behaves, and then I make predictions. And then the data-driven approach is bottom-up, and I learn by example. And I don't make any assumptions about how the thing works. I just analyze the patterns that I see and then project that into my prediction. So it's about predicting things. So I can predict a category, or I can predict a point. So maybe I want to say gold, no gold, or I want to say how many grams per ton. And when I want to predict the value of a point, that class is called regression, and I usually use regression. But these other methods here in the middle also can do things that look like regression. That's quite important, because regression, the regression we really understand is linear regression. And then we can do things to the data to make them look linear and make them look Gaussian and normal and whatever, and fit them to the methods we know and we understand. While these methods here are much less picky. They can simply work with what you give them. So that's why they're interesting, even though regression does regression quite well. And then, so if we want to predict a category, bin things into boxes, then we have either clustering, which is also interesting because it works with unlabeled data and works unsupervised. It just splits things into boxes. So I say I want things split into 7 boxes, and it does that, and then it tells me how good the split worked. And I can label things and teach it in a supervised process, and then I have a lot of different choices, which I won't go into detail. But that's kind of the taxonomy of machine learning. And today I will give you 3 examples of how we use some of these in a geological context. We're trying to either understand what they do or trying to get new insights. Certainly, one of the things you always hear in the context of not only statistics, but also machine learning is garbage in, garbage out. The output, the quality of the output you can get is never better than the quality of the things you put in, and the way you decide what you put in. And so you have to ask the question, is my data fit for the purpose that I'm trying? Is there enough statistical structure to make the learning process useful? And if there are any predictions, is there any scientific reason that it should work that way, or is it just the algorithm hallucinating something? And here, this is an interesting paper published in 2016, where the authors claim that they could train an algorithm to distinguish between criminals and non-criminals by just looking at their faces. And of course, it produced quite a stir because it has massive ethical ramifications if that worked. If you could just scan somebody's driver's license and then say, oh, well, Minority Report, there's a likelihood that you will commit a crime and we should do something. When you look at these pictures a bit longer, you will notice that the criminals don't have white collars, while the non-criminals have white collars. And the criminals are not smiling, while the non-criminals don't frown. So some people in the discussion, archive is open, so preprint, so the review process happens after the publication, which is very interesting. And people pointed out that, oh, well, when you look at those pictures, and they didn't present the millions of pictures or thousands of pictures they used, there's a difference. The authors then say, oh, interesting point about the colors. We tried that again by just masking the face and not looking at the color. But the frowning, smiling thing is a cultural thing. So Westerners see this as a difference, while Chinese don't interpret it in that way. Anyway, it was a good example of machine learning gone wrong, because the machine learning algorithm picked up something, but picked up the wrong thing because we fed it the wrong data. And so in terms of structure and structure, color, non-color, frown, smile, we fed it something that was not useful to make a useful prediction. So in the first case study of machine learning, I want to look at classifying rock types using hyperspectral data and on scans of drill core, and using geochemical data to train the algorithm. So just as a recap, hyperspectral scans, hyperspectral means scanning beyond the visible spectrum. In this case, many minerals have diagnostic features like absorption bands in the infrared, and then picking these absorption bands in an infrared spectrum can be used as a diagnostic feature to say this mineral is present, sometimes even in that proportion. So in this example, this is the spectrum of kaolinite, and so when you see these characteristic dips in the spectrum, you know there's kaolinite present. So scanning drill cores is fast and cheap. So that's quite attractive compared to taking samples, running them through an assay lab, and then waiting for the results to come back, and they're expensive. So the question was, can we use the sparse assay data to train our algorithm to then make this association between measured spectrum and measured chemistry? It's a fairly dense data set because we have vast numbers of scan lines and a lot of assay data. And this is a very simple model because it's just binning things into pigeonholes. We're not trying to understand why it's in the pigeonholes. We're just putting it into the pigeonholes. And this is a workflow of how this is then how this was used. So you feed a new bit of rock and you into the classification algorithm and see how it matches against our set of canonical samples. This is the labels. This is the pigeonholes. And then from that, we estimate the value we're really interested in, the chemical concentration, and also calculate the uncertainty. How certain are we that this prediction is correct based on how closely our measured piece of rock matches our canonical collection. If we're happy about the uncertainty, if you think it's a good match, done, fine. We can say, okay, this is what it is, and this is...
Sorry to interrupt. When you say, are we happy, do you mean is the machine happy, or are you as a person overseeing the science happy?
So as a person, I set a threshold and say, if the uncertainty is below a certain value, let it pass. If it's above a certain value, then I say, oh, we're missing this. This rock type is not in our collection. It doesn't match any of this closely enough, so we need to add something to our collection. And then we go into this branch.
So the human being is making that decision?
But not on every one, not on every scan line, but just on the human sets the rule. So this is the cutoff line. If it's better than that, let it pass. If it's worse than that, stop. Then we have to do something. And then we have to go into this part and characterize what's the chemistry, what's the associated spectrogram, add it to our lookup table, and then add it to our classification algorithm, and then play the whole thing again. Next thing comes in. Does it match? Is the estimate good? Does it satisfy our quality criteria? Yes, job done. No, oh, we need to add something more. But it actually worked quite well. What we could pick up in this set was a number of different rock types that the geologists from this mine knew were characteristic for specific processes, specific alteration processes, and we could then match the the calculated chemical characteristics, in this case potassium and sodium concentrations, our predicted concentrations matched the measured concentrations very well. And we could reconstruct those alteration trends. So it did work quite well in putting the rocks into the right pigeonholes, and it made pretty good predictions about the chemistry. So the geologists on this mine were very happy with this solution. It worked because it was quick, it was cheap, and it produced good results that were comparable to what they already knew about the mine. So in the second case study, we compared machine learning against classical geostatistics. Because we have geostats, why try something new? If we don't know what this does, but we know this very well. And we compared Kriging as a geostats method against random forest as a machine learning technique. And in this case study, we had a fairly big data set from the southwest of England with lots of chemical elements measured. Excluded were those elements which were known to be mobile or below detection limit, because that then doesn't give meaningful results. And we had quite a bit of so-called auxiliary data, so data that, like gravity, geomorphology, radiometrics, infrared satellite images, which are easy to obtain, dense, they're closed maps covering the entire area, compared to the still 600 sampling locations we had from this study across the southwest of England. It is a fairly complex model because it makes assumptions about the mobility of elements and also about the spatial correlation between elements. So, and it's sparse, a spacing of 4 kilometers between sample location might sound like a lot, but 600 data sets is not in the tens of thousands or millions range. It's far away from that. And what we wanted to do is identify geochemical outliers, which would be interesting for exploration. Not that we wanted to explore the southwest of England, but it was a handy data set. So that's the geological map of the study area, and quite distinct are these batholiths, these granites, and you will see them popping up again in the data sets. So here, this is some of the auxiliary data. We have the gravity, where you can see the granites are relatively light. They stick out as being lighter than the surrounding rock. In the radiometrics, you can see them again because they're a bit richer in radioactive elements than the sediments around them. And then here's 2 examples of infrared data from Landsat. One tells you about soil moisture, and the other one about certain clay minerals that are chemical weathering products. And I would think that most of you know about Kriging. You've heard about this as an estimation method that takes into account that things sometimes have a spatial relationship. So if I stand on a granite and I make a measurement here and I move across and I take another measurement here, they're very similar. And I can go over there and still quite similar. But then a bit further on, the similarity starts to go away. But then there's also some noise, which in Kriging terminology is called the nugget effect. So that's the offset here. And then this distance here is called the range. So how far can I go before my spatial correlation breaks down? And we looked at, this is two examples from the many elements in this survey, where in tin there's a low nugget effect and a reasonable range, while in rubidium the nugget effect, the noise level is quite a bit higher and the range quite a bit shorter. So here we have a good spatial correlation, here it's not so good. And that pops up in the maps. So looking at the prediction maps for tin, rubidium, there's some prediction and then there's some uncertainty. So the uncertainty here is pretty low, except for this spot. And this is because we don't have data. There are no data points. So the uncertainty is high. In rubidium, where there's a much higher noise level, a much higher nugget effect, it's generally quite noisy. So that's reflected in these warm colors. So random forest as a machine learning tool that can also produce regressions. The maps, you can see the granites again. And then it produces some uncertainty measures, which is the interesting part for us, because many machine learning techniques don't report uncertainty. So just take this in as this is what it tells us. But then when we compare these for tin, Kriging versus random forest, the prediction maps look rather similar. They're not too far apart, but the uncertainties are the opposite. And so if we understand what Kriging does, so we have here we have a low uncertainty because we have data, and then we have a high uncertainty because we don't have data. Random forest tells us the opposite. It tells us where we have data, we have high uncertainty, and here where we don't have data, we have low uncertainty. It doesn't really make sense. And it doesn't look much better in rubidium, except for here, random forest is a bit more confident about the rubidium prediction than Kriging was. So that's puzzling. In an exploration context, you rely on a measure of uncertainty to make your decisions, like investment decisions. Do you want to continue? Do you want to invest more money into this tenement? And if you don't understand what it's telling you, that is troubling. And what when we look at the predictions, when we sample from this map and try and make predictions, we can also look at the error that we then encounter, and we see that for the tin example, where we have a low noise level and long range, Kriging performs really well. It really outperforms random forest, while in the example of rubidium, where it's generally noisy, there's not much of a difference. So in the question of which method to choose, there are certainly situations where Kriging gives much better results, but sometimes it doesn't make much difference in the prediction. So that's a design decision what you want to do, but the uncertainty question is still puzzling. And then, as a
because the Kriging is considering the spatial distribution of where the data points are. but your random forest is not.
Yes, I think that the spatial correlation is really a key thing here, and maybe the way to understand the random forest uncertainty is to think of it as variability. So that's when it doesn't have data, there's no variability, and maybe it is apples and oranges. But since random forest is sold to us as something that does regression-like things and reports uncertainty, we wanted to see how does it compare, and nobody had noticed. So yes, the things you said are really important considerations, and we are still investigating that, but that will be something for different talk. Here, this is work that I was involved in with Nacho, where we looked at landscapes, and we had this idea that we can characterize landscapes through mathematical methods, like machine learning algorithms. Because as a geologist in WA, the landscape is not just flat. When you drive through it, you notice subtle changes, but it's very difficult to pin down what those subtle changes are, and whether you're just imagining this because you've been driving for too long, or whether these are real differences between landscapes. And so we started out with a satellite product called the Shuttle Radio Topography Mission, a radar topography mission. So this is a radar altimetry data set captured on one of the shuttle missions. It has a 30 meters resolution, which is fine when we work on this scale. We even downsampled it because we didn't need it in that resolution. This particular map is an expression of the flatness of the valley floors. The lighter the color, the flatter the valley. So you can see here this part of the Euclid Basin, which is very flat, and then this map is very white, while over to the west, where it becomes more hilly and more defined, then they're just fairly narrow valleys and the hills. And as input data, we started with this elevation map from the Shuttle Radar Topography Mission, and then added things like the valley bottom flatness as a derived parameter, ridgetop flatness, slope classification, wind exposition, and wetness index. These are all indices you can derive just from the geomorphology. And then we gave these data to a classification clustering algorithm, the one on the top of that tree diagram, and said, divide this up into 7 classes, because Nacho and myself, standing in front of big screens, decided that there should be 7 classes of landscape in this area. So we meditated over this map for a long time, and then eventually came to the conclusion that we saw 7 different classes. What would the algorithm see without us supervising it, without us telling it? So these amorphous blobs, these lines, is where Nacho and I saw different landscape types, and in this color map, this is what the algorithm thought were different landscape classes. So yes, okay, so there's something here, then there's something through here, but then it's a bit patchy over here and patchy over here, and doesn't quite match what Nacho and I saw. But it's an interpretation, and when you resample this and use the compare it with predictions of what it should look like, you get an 84% accuracy. So it's a pretty good match, but not great. So next round we told the algorithm the classes. This here, here, here. These are different landscape classes. Map them onto the landscape. So you see it has some similarities with what you saw before. And if you then sample it and simulate it and compare the predictions of what you think the landscape should look like in a certain pixel, here we get to 94% accuracy. So it looks like there is more to the landscape than the unsupervised algorithm picked up. And if you leave out some parameters, the prediction accuracy also goes down. So the question was, okay, so it gives you a better match, but is this actually true? So when you then use a different regression technique here, principal component analysis, we thought that this blob here and that blob here would be different landscape types, while in the sorry, I forgot which of the algorithms we used here. It looked like they would simply be the same. But when you look at the principal components, it looks like they do split up into separate populations. So it does look like what we interpreted as being different landscapes actually are different landscapes. So it's not something we hallucinated. It's not something the computer hallucinated. This is something we want to explore further. But it shows you that you could use these mathematical techniques to interpret landscape at large scales, where to the human eye it tells you there is something, but it's very difficult to pin down. And this looks promising, that it will give us tools that we can use to differentiate landscapes, associate them with underlying geology, and then apply this to other landscapes like Western Australia, where sometimes the geomorphology is not too exciting, but there's actually more in it than you would expect. So what did we learn from this? Can we teach geology to machines? And I think we should ask the question, are we using the right tool for the question posed? So if we are in a problem statement that deals with high density data, high dimensional data, that we're looking for patterns, there's a simple causality and we're not making assumptions. So like the pigeonholing rocks into buckets, we might be after an engineering solution rather than understanding why certain rocks belong into certain buckets. Machine learning does a good job. But if we're in the world of sparse data, maybe low dimensional, we're looking for outliers rather than the patterns, so the irregularity rather than the regularity. We have to rely on models to make predictions. We look ultimately for an analytical solution to formulate and our understanding of the system. Then geostats still does a better job. So that's how I would split the problem space. Is it lots of data and more an engineering solution? That's certainly on the machine learning side. If it's few data and you're more after understanding what it does, then classical geostats will serve you better. So in summary, can we teach machines geology? It is a powerful and versatile tool, but not every problem is a nail. So you have to decide whether this is the appropriate tool for your problem statement. Geology is often data sparse. That limits what you can do with machine learning. But when you have a data-rich application like hyperspectral or potential fields or imaging techniques, then you get into the field of machine learning, where machine learning has its strengths. But what we certainly need to do is do more research to understand how machine learning performs in the spatial context. This is not really understood. And then that is connected to this question of uncertainty. What does the uncertainty reported by machine learning techniques tell us in the spatial context? And how does this impact decision making? And there's a lot happening, so it's worthwhile watching this space. So even if machine learning doesn't work for you now, maybe in 2, 3, 4 years' time, things have changed and it suddenly becomes interesting again. And so I'd like to thank you for listening. I hope you found this interesting. And I think we still have a little bit of time for questions before you get kicked out.
Please, thank Jens Klump.